Hi there, this video is for section 8.2. I'm going to show you how to find the surface area of a solid that's formed by rotating a part of a function, a length of a function. We actually did a very similar thing in a previous chapter where we found the volume of a solid formed by rotating a part of a function around an axis. So you rotate around there, you get this sort of three-dimensional image, and we sliced it up to find the volume of each individual slice, added them all up, found the total volume. Very, very similar in 8.2, except that we're going to be slicing up and finding the surface area of each slice, adding up all the surface areas to find the total surface area of this rotated three-dimensional object. All right, so let's jump into it. So just a couple quick notes here. If we have some sort of function, I'll draw some little random, graph here, math people love. And we revolve it around, let's say I'm going to revolve it around this axis right here, the x-axis. We end up with an image of our graph down below. So you can imagine like whatever distance that is, it has to have the same distance down here. So kind of make a mirror image with distances about the same. So it should go like this. And then we get a three-dimensional object. And we're going to take a little slice. And we're going to rotate it around. And that gives us like a band, a cylindrical band. You can kind of make out my poorly drawn picture here. Hopefully that's close enough that you get the idea. We're going to find the surface area of that band, and then we're going to add up all the surface areas. So we're slicing the function, rotating it around, finding the surface area of that slice, adding all the slices together. So what is the surface area of a little cylindrical band? Well, just from your algebra, from your geometry, surface area is just 2 pi r times its height. Our height here is going to be ds because we're slicing the function, not slicing the x-axis, not slicing the y-axis, slicing the function. So along the function, if you remember from the video in 6.1, if you had a chance to watch that, a small distance along the function is called ds. So we're going to be taking a sort of a height of ds or a width of ds, and the cylinder would be 2 pi r times that ds height. So that's just a slice. So to find the entire surface area, we just integrate all the slices. So this is the formula for the surface area. You integrate from whatever limits you have, beginning and the ending of our region, our function, and 2 pi times the radius times the height ds. Okay, so let's go ahead and see that in action. So my first example here, a segment of the function y equals 2x squared is defined to be from 1 comma 2 to 2 comma 8. Find the surface area of the solid form when the segment is rotated around the x-axis. Then find the surface area when it's rotated around the y-axis. Then find the surface area. So there's 3 problems here in A. So we're doing the same thing, but we're kind of doing 3 different revolutions, 3 different rotations, and we're going to find the surface area of each of those. So just to help people with a visual aid, it's not necessary, but sometimes it really helps people when they're seeing what's going on here. Y equals 2x squared is some parabola thing. It does not need to be accurate. You can use Desmos if you want it to be accurate. We are going from 1 comma 2. So this is when x equals 1 and y equals 2. So do that different color here. X equals 1, y equals 2. So that's the beginning of our function, of our length. And then we're ending at 2 comma 8. So this is going to be x equals 2, and this is going to be y equals 8. So we're going from 1 comma 2 to 2 comma 8. We're doing this segment right here. Even though I have a little segment down there, we're not using that segment. So we're just doing that segment right there of the parabola. And then the first part, I'll do this in blue. It says the segment is rotated around the x-axis, and again, we're looking for the surface area. So find the surface area when we rotate around the x-axis. So this be the x-axis right here. So I take my little slice, just like in my example of the formula idea up there. I take this little thing. The distances have to be equal. So what distance I was up there, the distance down there. So I'm going to rotate this little bit over here, and I'm going to get a little cylindrical like band, a little cylindrical slice there. I don't need to draw the whole thing. All you do is figure out the surface area of one slice and then add up all the slices. So once you get one slice down, you put the integral sign, you add up all the slices, you're good to go. All right, so we know what the surface area is. Surface area is equal to, well, let's do the surface area of a slice just to emphasize the slicing idea. Surface area of a slice, well, for that one little slice, it would be 2 pi r times this thickness, this width, s. And we need to figure out what the r is. The r, the radius of any circular object, is defined to be the distance from the middle to the outside, the radius, right? The radius goes from the middle to the outside of any kind of circle thing. And so if I go from middle up here, that's a vertical distance. So it's a y type of distance. Is it y? Yes, it is. Y is defined to be the distance from the x-axis up to the function. So that is, in fact, just y. So I got the surface area of a slice. Surface area of a slice is 2 pi times y times ds. So now to find the total surface area, well, I just integrate. Now I have the choices. From 6.1, if you had a chance to do that assignment, ds can be written in terms of the differential dx, or it can be written in terms of the differential dy, and it is really up to you which way you'd rather do it. So if we write it in terms of x, for example, so for x's, the formula for ds is 1 plus the derivative squared. And a lot of people default to that formula, which works perfectly fine here. So I'll show you that one. Now, the differential tells us what variable we're using. The differential is dx. So everything has to be in terms of x's. So the limits on my integral have to be in terms of x's. So that would be x equals 1 to x equals 2. Those are my x values, my smallest and largest x values. And this y also has to be in terms of x. But we know how to do that because y is just 2x squared. So we would write this as the integral from x equals 1 to x equals 2 of 2 pi times the y function in terms of x times square root of 1 plus dy dx. I got to find dy dx. So what is dy dx? So remember up here, I have y is equal to 2x squared. So if I differentiate with respect to x, the derivative of 2x squared is just 4x. So this would be 1 plus 4x squared dx. And now everything's in terms of x's, and so now I'm ready to anti-differentiate this thing. This works by hand. You have to use a trigonometric substitution to do it by hand, but I'm just going to use technology because I'm not trying to focus on integration techniques in this video. I'm trying to focus on how to find surface area, how to set up the function, how to understand how slicing works. So I'm just going to default to technology to find the answer to this surface area integral. All right, so I'm going to jump over to Wolfram Alpha. That's my go-to algebra engine, and I have to just type this whole thing in here. So integral of, I did this from a previous video. Integral of, I have 2 pi times, so now I have to flip back and forth because I'm not going to remember half of it. 2 pi times 2x squared times the square root. 2 pi times 2x squared times the square root, and that was 1 plus 4x squared. And let me just use some more parentheses just to make sure that it has a better chance of understanding what I'm trying to talk about. So it's the square root of 1 plus 4x squared. And then that's going to be like a dx. And then from x equals 1 to x equals 2. And let's see if I typed it in close enough for it to figure out what I meant. Integral from 1 to 2 of 2 pi times 2 times x squared times the square root of 1 plus 4x squared plus dx. I do believe that is correct. I'm just going to double check real quick so I don't make a mistake. 2 pi. I don't know why I put an extra parentheses. Maybe I put the parentheses there, but the 2x squared is the same as 2 parentheses x squared. Okay, so I think I got it close enough for it to get the right thing there. 2 pi 2x squared, 2 pi 2x squared, square root of 1 plus 4x squared. Square, yeah. Okay, so I typed it in right. And it gives me a total surface area of about 190.84. You can see some inverse trig stuff that they did in order to do it in terms of a formula, but I just want the answer 190.84. So 190.84, and I guess I should do wiggly approximately equal to 190 because not exactly equal to 190.4. So that's an example of how to find surface area of some sort of length along a curve rotated around an axis. Okay, I'm going to rinse and repeat a couple of times here. Same function, y equals 2x squared, but we're now going to find the surface area rotated around the y-axis. So going around the y-axis this time. So let me just make some more space. So for my drawing, I'm going to be doing the same curvy thing from 1 comma 2 to 2 comma 8. I'm going to be doing a little slice of the thing, but now I'm rotating around the y-axis. So I get this slice over here. That's my little cylindrical band. And then so we're doing about the y-axis. Then our surface area, once again, is going to be, I'll just do total surface area. I'll just jump the ship here. It's going to be the integral of the slices. Each slice is 2 pi times r times how thick it is, which is ds. So that's our total surface area. We just take a slice, which is 2 pi r times ds, and we add them all up. So that's our surface area formula. Now we need to put ds in terms of something. We can put it in terms of x or y. It doesn't really matter. So we can put it in terms of either one. I'm not sure what people's sort of intuition would be. Maybe because we're doing it like horizontal rotation, maybe we should put it in terms of y. Let's see what happens if I do that. So if I put it in terms of y's, I had to put y values here and here. The smallest y value is 2. The biggest y value is 8. And then I get 2 pi. And the radius, what is the radius? The radius always goes from the center of the function to the exterior, to the outside. This right here is the drawing for this problem right here. So here's the center, and I go all the way out. And that's a horizontal distance. A horizontal distance is an x distance. Is it x? Yes, it is, because x is defined to be the distance from the y-axis all the way to the function. So this is going to be x. And then I'm going to do times ds. And I'm putting it in terms of y. So I'm going to use the y version of ds. You remember from 6.1, there's 2 versions of ds. One in terms of x's and one in terms of y's. So the one in terms of y's look like this. I get a dy here. Because it's a dy, everything's got to be in terms of y's. I already have my limits in terms of y's. This is not in terms of y. I need the x turned in terms of y, and I need this thing in terms of y as well. So I need everything in terms of y if I'm going to use the dy version. Okay, so how do I get things in terms of y? You may be asking. Well, we know the formula, y equals 2x squared, and we could just convert stuff, right? So I can divide by 2, or let me get x first. So I can divide by 2, y over 2 equals x squared, which gives me x is equal to plus or minus square root of y over 2. Now you can tell from our function, from I guess from our graph, if you want to look at our graph, that the only things we get are positive x values. Our function goes from here to here. It goes from positive x equals 1 to positive x equals 2. So there's no need to have a negative, right? So no negative x's. So we can ignore the fact that it's plus or minus and just take the plus version. So we have x equals square root y over 2. and that would go in for there. So now we can put x's in terms of y's. It's just square root y over 2. How do we find dx dy? Well, you can just differentiate this function right here. Dx dy, whoops. I'm differentiating with respect to y, so dx dy is equal to, well, this is a square root thing, so I get 1/2 y to the minus 1/2. And then I still have my over 2 thing here. So that's my dx dy, and I can just put that into this thing right here. I guess I would write 1/2 over 2 as 1/4, just to make things look a little easier to deal with. So my area is 2 to 8. 2 pi x has to be in terms of y. So that's square root of y over 2. And then I have the square root here of 1 plus dx dy is, I'll just write it as y to the minus 1/2 over 4. I guess I could write the y to the minus 1/2 in the bottom. So there's a lot of ways of making this look different, and I'll let you choose which way you want to make it look. And I still have dy. Oh, I forgot to square this thing because it's dx dy squared. Dx dy. So I found dx dy, I got to square it. So it's the square root of that thing. So now this all is in terms of y's. Everything is in terms of y's. I can just pop this into my algebra engine, and I can get the total surface area. Now, if you were a person saying, hey, I just want to put everything in terms of x's, let's do it in terms of x's. So we got the surface area is equal to 2 pi r times ds. Let me put a big like or here. So if people look back at these notes, they're like, what is he doing here? I'm doing it a different way. So some people would do it in terms of y, some people do it in terms of x's. It's really up to you. It works both ways, every way, every time. So the question is what's easier in terms of for you personally to think about, and also what's easier algebraically to compute. So in this other version here, I'm going to put everything in terms of x's. So I need x values here. The x values are 1 to 2. And I'm going to do r. Now, r, we're getting the same darn thing, right? R is the distance from the middle to the outside. That's what radius is for every circle. Start from the middle, go to the outside. So it's still x. It didn't change, right? It's still 2 pi times x, right? Just because I'm putting things in terms of a variable doesn't change the fact that the radius starts in the middle and goes to the outside, and it's a horizontal distance x. This is going to be square root of 1 plus, instead of dx dy, we're going to do dy dx because we're using the x version. This gives me a dx here. By the way, I know what dy dx is because we did it over here. We did it, it's 4x. So in this particular problem, we get 1 to 2 pi x square root of 1 plus 4x squared dx. Again, user experience will vary. My personal opinion is if for this specific problem with this specific function, it looks like the integral in terms of x's happens to be easier. So anyway, that you can do whatever you want. You can experiment, see which one's easier, and choose which one you like. And they give you the same answer. They give you the same answer. I know there's some completionists out there who want an actual number. They're not satisfied with just the integral. So I will type this into my knowledge engine, my algebra engine, to get an answer for those people who want a number. But from my mathematical point of view, we've solved this problem except for typing it into a computer. All right, so we got 1 plus 4x squared. We have x, we have 2 pi, that kind of thing. Okay, so 2 pi, I'm just going to cheat and change this. 2 pi x. So it's integral of 2 pi times x times the square root of 1 plus 4x squared dx from 1 to 2. Let's see if it figures that out. 2 pi x square root of 1 plus 4x squared dx from 1 to 2. Let me just double check. 1 to 2, 2 pi x, 1 plus 4x squared. I think I got it. So I didn't have to modify much to be able to do that one. And so 2 pi x, oh, here it's 2 pi x, 1 plus 4x squared. Yeah, that's what it is. So 59.422. Okay. 59.422. All right, so that would be the surface area if we revolved around the y-axis, around x equals 0. All right, so let's see. There's one last question. So we did the one where the segment is rotated around the x-axis. We did the one where it's rotated around the y-axis. So what's our last goal here? Find the surface area is rotated around the line x equals 5. So x equals 5. So we're going to find now the surface area when it's rotated around this sort of non-standard axis of x equals 5. All right, well, let's get a quick visual picture of what's going on here. So my function again, 1, 2, 2, 8. My function is 2x squared. Goes from here to here. I'm revolving it around the line x equals 5. Where is the line x equals 5? Well, this is the x-axis right here. So x equals 5 is 1, 2, 3, 4, 5 over here maybe. So this is my axis of revolution. I can draw a straight line. Right, so I'm going to take a small slice of my function. I'm going to rotate it around. So the distance from here to here should be mirrored. So I need the same distance over to here approximately. And I get my little slice over here. And then I draw my little cylindrical band. It doesn't look great, but hopefully you see what's going on here. The sort of width or the thickness of the cylindrical band is ds because it's a distance along the function. And then I need to figure out the surface area of that guy. Surface area formula, it's going to be the surface area of a slice added all up. I guess this goes a little further, but whatever. So the surface area is going to be, well, for a slice, it's 2 pi r times the thickness. But for the total surface area, it's just going to be the integral of this thing. All right, so I'll put everything in terms of x's again, just for fun. 2 pi, we're going to do something in terms of x's. That's going to be the radius here. And then the ds I'm going to put in terms of x's. The version in terms of x's has dy dx here. And dx over here. So I need everything in terms of x's. So the limits on the integral have to be in terms of x's. And everything else has to be in terms of x's. We already know how to put the derivative in terms of x's because from before, well, I'll do it again. Y equals 2x squared. The derivative is just 4x. So I know I can put the 4x in for dy dx and then square it because it's dy dx squared. Now I have to put the radius here in terms of x's. Well, what is the radius? The radius is always the distance from the middle to the outside. So there's the middle to the outside. It's not exactly symmetrical, my little band, but I think you guys get the idea. So that's my radius right there. The radius is a horizontal distance, right? That's a horizontal. So it's got to be some version of x. Is it x? It is not x because x always measures from the axis to the function. That is x. So how do we find the radius if it's not x? I mean, it's a horizontal distance, so it's kind of like an x thing. But x as a variable is always from the y-axis out, right? So I mean, this is 1 because we started at 0 and went to 1. We started at the y-axis and we moved over 1. That's why x equals 1 is right there. This distance right here is our radius. So how do we find that distance? Well, some people are kind of thinking about how it works out. Maybe some people already figured it out. But let me remind you, if you're trying to find a distance between two things, you could just subtract. So we know the total distance here is 5. How do I know that? Well, it's labeled 5, right? This total distance here is 5. We know this little distance is x. So you have 5 is the total distance from the y-axis. X is this little smaller distance from the y-axis. So what's r? It's just got to be the 2 subtracted, right? So r is equal to 5 minus x. All right, so that means we have 5 minus x as our radius. And now we're going to put everything in terms of x's and then do our antiderivative or integration. And we are all set for the last surface area calculation. dy dx we know is 4x, so this is just 1 plus 4x squared. And there's a dx here. The dx is not inside the square root. All right, so if we just do this computation, we will find out the surface area when this length of the function is revolved around the line x equals 5. And it's just very similar. You just got to figure out the radius. You just got to figure out the slice. You got to decide whether to put it in terms of x's or y's. Some decisions to be made. But once you get the hang of these problems, you'll see that, you know, whatever try little differences they throw in, it's basically the same kind of thing each time. All right, so let me get a number for you folks who want numbers. 2 pi, we got 5 minus x, and we got the same square root thing. So I think I can just change my thing right here. 2 pi, instead of x, I'm going to have 5 minus x, because my radius changed to 5 minus x. And then I still have that square root thing, 1 plus 4x squared, and it's still going from 1 to 2. So all I do is just change the 5 minus x there, and I'll do my computation. There's the 2 pi 5 minus x and my same ds thing right here. And I get 131.77. Approximately that surface area. All right, so those are surface area problems. I do have one more here if you'd like to give one a try. I hope people do give this a try because it's kind of nice. And I also have an opportunity for you to practice your anti-differentiation by hand. You don't have to do it if you don't want to do it by hand, but it might be nice just to keep those skills, you know, sort of current. So what we did here in A, there's 3 parts to A, you know, different surface areas depending on which axes I revolved around. In part B, you can use that knowledge to see if you can find what happens when we take the segment of y equals 25 minus x squared that's rooted from -5 to 5. We revolve this around y equals 0 and find the resulting surface area. And as I said, this problem is nice to do without technology, so you can give that a go if you want to practice that as well. So if you're willing, you know, sometimes it's really nice just to try things yourself and see if you can get it. Or if you do get stuck, that's totally fine. This is called learning. But then you know where you get stuck, and you could say, okay, that's where I'm getting stuck. Let me see if I can see from, you know, Jim's solution process how I can get unstuck. And maybe that will help you in the future when you get stuck on another problem. You're like, okay, and when I got stuck before, this is what I did. Perhaps you can do that again and be more consistent, more successful at solving these types of integral problems. All right, well, hopefully folks have paused and given it a try. And now I'm going to show you my solution. All right, so I will draw some random function just to give us a visual picture. I actually know what this looks like. If you did use Desmos, I know some people like using a graphing calculator, whether it's Desmos or something else, to graph things. It does look like this, kind of an arc like this, sort of like a sine wave. It's actually a half circle. It goes from -5 to 5. So that's the function y. And we're going to be taking a little piece of it, and we're going to rotate around the line y equals 0. This is y equals 0, also known as the x-axis. When I rotate this around, I get an image down here, and I get my cylindrical band. And we already know what the area of those things are. The area is 2 pi r times the thickness ds. And then that's just for a slice. And to get the total area, we integrate. And that's how we find the area of our, you know, the surface area of our object. All right, so I'll put everything in terms of x's again, just because it ends up being a little easier for this problem once again. So the smallest x value is -5. Largest x value is x equals 5. 2 pi, I got to find the radius. So the radius goes from the middle to the extremity. So here's the middle. The axis of revolution is where you're always going to find the middle, because that's where it's symmetrically revolved around. And the outside is up here. That's a vertical distance. So a vertical distance is always some sort of y distance. So is that y? The answer is yes, it is, because it goes from the axis to the function. That is what y is defined to be. And then we're going to use a version of ds, as I said, that has x's in it. If you use the version with y's, it works out exactly the same way, just a little bit different algebra. So totally fine if you did the dy version instead of the dx version. All right, so we need to put everything in terms of dx's. Remember, our differential tells us the variable we need to put everything in terms of. So we're going to put everything in terms of x's. So we get -5 to 5, 2 pi. We need to not have y here because it's got to be in terms of x. So how do we change y into x? Well, we know how to change y to x. I mean, that's the function, right? Y is equal to square root 25 minus x squared. So this is going to be 25 minus x squared square rooted. I guess I should write to the 1/2 power, but you know, that's the same thing. And then I multiply by the square root of 1 plus the derivative squared dx. So I'm going to have to find out the derivative. So let me write down the function here. Y equals, I'll do it to the 1/2 power since our formulas work with numbers, not with weird symbols. So there's our function, 25 minus x squared to the 1/2. So its derivative, dy dx, will be 1/2 of this creature. A little bit. 1/2 of this creature to the -1/2 times the derivative of that inside function. This is called the chain rule, right? So the inside function, or the critter I called it before, I guess, right? 1/2 times that thing to the -1/2 times the derivative of that thing. So dy dx is, I'll write this on the bottom, 1 over 25. Oh, there's a 2 down there too. 1 over 2, and then 25 minus x squared to the 1/2 power. I guess you don't have to write on the bottom, but I just want to get rid of the negative exponent like that. And the derivative of 25 minus x squared, derivative of 25 is 0. Derivative minus x squared is minus 2x. Looks like my 2's are going to divide out. So dy dx is going to be, let's see, the 2 divides out with the 2, or cancels, as people like to say. And then minus 1 over this 25 minus x squared to the 1/2 is what my dy dx is, and that goes in for the 1 plus dy dx squared thing. All right, so let's put that derivative in there. Looks like I need some more space. So let me just back this up a little bit. All right, so I got to put the derivative in there. Oh, I already have my 1 plus. I have 1 plus 1 plus 1 plus. Okay, I got lost. Let me get found again. All right, so it's 1 plus my derivative being squared, and my derivative is -1 over 25 minus x squared to the 1/2 power. I think this is more difficult to write than actually to solve. I mean, it looks difficult to solve too, but you'll see it's actually quite nice if you just simplify it algebraically. All right, so I did my formula, 2 pi times r times ds, my ry, which I converted into 25 minus x squared square rooted. And then I had the square root, my ds, which was the square root of 1 plus the derivative squared, times dx squared times dx. So 1 plus derivative squared dx, I had to find the derivative, which was this guy over here. And then I have to do that squared times dx. Now, for those of you who did try this without using technology, awesome. Let me show you what a nice way of simplifying this. Remember, there are no real tricks to doing antidifferentiation. You just basically need to simplify it algebraically until it looks like something you know how to do. So it just is a great time to practice your algebra techniques. There are algebra techniques called U substitution and integration by parts and partial fractions. Those are all algebraic techniques. So some combination of algebraic techniques, whether they were learned prior to calculus or in calculus, is what we're looking for you to be able to practice. I'm going to again write this to the 1/2 power. Not sure why it's up a little bit. I'll just leave it there and write the 2 pi up a little higher so it doesn't look weird. So there's 2 pi, 25 minus x squared to the 1/2. Then I get the square root 1 plus negative 1 squared is positive 1. 25 minus x squared to the 1/2 squared. A 1/2 exponent squared will undo each other, right? Square root being squared just gives me the function. So this is 25 minus x squared. And then I have a dx sitting over here. All right, still kind of a mess, but I'm just going to simplify this some more and I'm going to keep simplifying it until I get a nice thing to anti-differentiate. All right, so -5 to 5, 2 pi. I guess I can put the 2 pi on the outside, right? Because I don't really care about the 2 pi. 2 pi got here. And then 25 minus x to the 1/2, x squared to the 1/2, squared to the 1/2. And then I get the square thing. So the way I'm going to simplify the square thing is I have a 1 plus a fraction. So I want to add those together. One's a fraction, one's a number. I can't really combine things together that don't appear to look the same. So I'm going to make this into a fraction. So like 1/1. So I'm going to be adding the fraction 1/1 to the fraction 1/25 minus x squared. So I have to get common denominators to add two fractions. So instead of writing this as 1/1, I'll write this as 25 minus x squared over 25 minus x squared. Why am I doing that? So I have the same denominator. That's the same as 1. Same thing over itself as 1. But now I have the same denominators. I think I made a mistake. Did anyone notice my mistake from before? So this 1 is a mistake. And I'll show you why. So when I was calculating my derivative, right here, I took 1/2 times the function to the -1/2 times the derivative of the function. That's all correct. I differentiated, I got this thing right here times -2x, the 2's divided out. And what results is not a -1, but a -1x. I forgot my little x right here. So this should be -1x being squared. -1x times -1x is +1x squared. So this should be +1x squared. All right. As you know, I don't like to edit out my mistakes because gosh darn it, we all make mistakes. And I don't want to hide the fact that even though I'm doing math for 40 years, I still make mistakes. Maybe that's a bad thing. You can judge me if you like, but that is the reality doing math, right? You're never going to do it perfectly. So that is what happened. I found my mistake. I fixed it. All good. Let's keep going. All right. So I'm just going to have to rewrite this thing because math people like things written over and over and over again. Okay. So what about the square thing? Well, it has a common denominator. So I can put 25 minus x squared as the denominator. When I combine the numerators, I have 25 minus x squared plus 1x squared. And you might be able to see that minus x squared and plus 1x squared add to 0, right? So I'm left with just 25 on the top and dx. And I'm really almost done. You're like, oh, this is taking forever. I think actually could be true, but we are almost done. All right. So when you square a fraction, you can square at the top and square at the bottom. So the square root 25 is 5. And the square root of 25 minus x squared, I don't know what that is. There's no distributive property with square rooting. You cannot write this as 5 minus x. The best we can write it as 25 minus x squared to the 1/2. That's the square root of that critter. But you may notice, maybe, that we have the square root of 25 minus x squared here on the denominator, and we have the 25 minus x squared to the 1/2 on the numerator. These are identical. If I divide two identical things, I get 1. So all I'm left with here is 5. Okay. So, I kind of set it up so that maybe it comes out kind of nice. So what do we got here? We got 2 pi integral from -5 to 5. All this stuff goes away except for 5 dx. I guess I can move the 5 outside as well, but I don't really care. The integral of 5 dx is just 5x. So again, the 5 you can move outside if you like. Goes from -5 to 5. And I'll just do the numbers. I get 2 pi times, when I plug in 5, I get 25. When I plug in -5, so I do, when I plug in 5, I get 25. When I plug in -5, I got to subtract that. So I plug in 5 minus when I plug in -5. When I plug in -5, I also get 25, but -25. So plug in 5 minus when I plug in -25, that's 25 minus -25, which is 2 pi times 50, or 100. And that is the surface area of this function, at least this part of a function, this part from -5 to 5, when revolved around the x-axis, around the line y0. That does actually form a circle. So if you know your geometry, you know that the surface area of a circle is 4 pi r squared. So we can actually compute 4 pi r squared for this particular function, trying to get this centered. And you can verify that 100 pi, in fact, is the surface area of the circle. I don't know, I thought it might be fun to do a shape that we actually can double check using our classic geometry formulas. But the point of this section right here is to practice our slicing methods and finding the surface area of some solid that's formed when I take a slice, or take a length of a function and rotate it around an axis. So hopefully this video was helpful for you understanding how that works, how slicing to find the surface area works out according to these formulas. And if you have any questions or want any help anything, please do reach out. And I hope you have an enjoyable day.